So, hello ladies and gentlemen, I'm glad to greet you all here today. And today, in the first lecture of the reinforced learning course, we shall discuss how do we actually make Q-learning applicable to some kind of continuous environment. So, we shall speak about approximate Q-learning and about deep Q network, which is actually named DQN. You can see it on the slide. So, today we come into the continuous world. And let's begin. So, today our outline will be rather straightforward. We just take the MDP, Markov decision process, the environment we are interacting with, and just discuss how to make our network, our model in general, be capable of dealing with continuous environment. But to do that, first we need to recap all the necessary instruments we already know. So, once again, we have this cumulative reward, discounted reward for the whole session, since timestamp t to the end of the session. We assume right now that the session will end eventually at some moment. And we have some kind of policy p, under which we have the q function, which actually delivers us the expected cumulative reward from state s and so on if we perform action A right now and perform according to the policy p afterwards. So we have only one additional free step right now. Ignoring the policy, we select action just here and now as the argument. And we have the value function corresponding to the policy as well. So it gives us the cumulative reward from this state and so on, but without this freedom to select only one action. So that's kind of it. And of course, we can rewrite the q function as the q function and q function as the value function as well. So here we go. Q function from state S with action A is actually expected reward for action A in state S plus gamma multiplied by value of the next state where we actually get transited to under the policy P. And because we can write value function as the expected value of the Q function as well, so we do that. Q function under the policy P is the expected reward for action A in state S plus gamma multiplied by the Q function of the state T plus 1 and action T plus 1, where we have this state and action coming from this expected value. You see? So here we go. And when we have our Q function and value function, we can actually define a policy, because if you have a Q function, it shows you how good is any action in any state. So we can simply select the best action in every state, perform it, and here is our policy. Of course, it has some problems, because if we pick always the best action, we ignore exploration. We only exploit our policy. That's why on the previous classes we discussed how to make it a bit more explorative. For example, add some epsilon noise, epsilon greedy strategy, where with small chance of epsilon we always perform randomly, and with chance 1 minus epsilon we select the best action. Or we can apply the softmax normalization to the q values, so actually q function is defining some kind of probability distribution over different actions. But nevertheless, if we have some policy assigned with our q function, we can actually say that there always exists some optimal policy, which q function will be always greater or equal to our current policy. And actually, if we meet the requirement, if we meet this equation, if our policy q function is equal to the optimal policy q function, then our policy is actually optimal. And from it, we can actually get the Bellman, we get this result from the Bellman optimality equation. So our optimal policy is, our optimal q function is delivering itself from this equation, expected value over state S, reward from state S, plus maximum over all the actions, q function in state T plus 1 and A prime, action A prime, over which we get the maximum. And from this actually optimality equation, we deliver our training strategy. So what's going on? We know that for optimal strategy, this equation will be actually true. So we'll get the equation. It will be equal. But for non-optimal strategy, we can actually see that when we add a bit of information into our q function, when we incorporate new reward we got just right now from the environment, and new information on the state to which we got transited using action A in state T, in state S, T, we actually update our q function to make it better. So, just in case, here is our q function, here is our update step. So we have our q function, and we say that after we get some information, we take the reward we got after interacting with the environment, plus gamma multiplied by maximum over all actions, Q function of the next state and best action. Actually, this is the value function of state t plus 1. And if you take a look at this formula, you can actually see that it's almost the same formula we've written on the last class. So, look, what do we have here? Q function of state S and action A, Q function of state S and action A. Actually, we can take it out from here. So Q function with multiplier 1 minus alpha plus alpha multiplied by what plus gamma maximum Q function blah blah blah. So actually here is exact the same exponential smoothing we had in the last lecture. So it's 1 minus alpha current Q function plus alpha multiplied by new value of Q function. You see, it's just written in different form. And if you take really a look here, you can see that it looks really familiar, because this is exactly a gradient if we use the mean squared error minimization. So look, if we say that we have some kind of Q function and new estimation of our Q function, and we have some kind of learning rate, constant learning rate, then if we get the derivative of this last function, then you can see that it's actually 2 multiplied by r minus gamma by value function minus Q function. So r plus, plus gamma by value function minus Q function. We have exactly the same values here and here. So actually this is not just some kind of heuristics used to create an update rule. This is just a gradient of the mean squared error loss minimization. And actually this is just gradient descent, as you can see it. But in here one can actually see some kind of a problem. What if we're speaking about Q function in general as some kind of function, which just takes the state and the action as the input and predicts some kind of output? Then we can actually see that in here, when we get the derivative of the last function, we have Q function both on the left and on the right. And actually, to have this exact derivative, we need to make a kind of strange but really strong assumption. We need to assume that this Q function is actually constant when we get the derivative. So it does not affect the derivative. Actually, it is some kind of, it's correct. It really requires some additional mathematics to explain explicitly why is it going on. I suggest either to share some additional links. It will be about 2 lists of paper, 2 pages to read about that, or we can discuss it on the webinar explicitly. But in general, what I can say in here, take a look just at this formula. So we have our current value of the Q function at this moment, and we have our new Q function, which should actually be more informative because it incorporates new reward and new state, information about which we just got right now. But this is our estimation of the quality of the next state from the current point of view, but it's in the future. So we use our current Q function to estimate the quality of the future state. That's why it's kind of in the future, and we actually assume that future does not affect our current value of the Q function, so it doesn't give us any kind of derivative. It's just kind of intuitive explanation. I hope it helps at least a bit, but of course we can discuss it, and we should discuss it deeper, but with some mathematics, right, and so on. So otherwise, our exponential smoothing from the last class is actually equivalent to gradient descent minimization using the mean squared error loss. And looking here, we finally can ask a question. If we have some kind of environment where we have an image, for example, like in Terraria, Space Invaders, we have the state, which is actually an image. How many states are there in this particular case? Approximately 2 in power of 210. It's actually height by 160, width by 8 by 3, because actually we have 8-bit color map and we have 3 colors, RG and B. So kinda really a lot of different states. And definitely we won't be able to create a huge table for our Q function where for every state we've got some kind of values for all the actions. And here we have only several actions like left, right, fire, and I guess that's all. So we have really small number of actions and really huge amount of states. So instead of trying to learn the Q function as some kind of table, we actually can assume that we are now working with continuous state. So we're just working with some image, vector, or tensor, something. which represents the state, and then actually nothing changes. We still have our loss function, which is actually loss between true Q function, our new estimation of the Q function, and our current Q function. And actually we can assume that this is quite a good approximation of our true Q function. And actually that is actually true for Bellman-Applicability equation as well, because when our Q function converges to the true Q function, we get zero loss because our Q function is actually equivalent to the true Q function. So we don't get any new information. That's why our Q function from state S and action T will be exactly equal to reward plus gamma by maximum over all actions of Q function in the next state and so on. So actually we'll converge to some place and we can do that. So what do we have here? We have an environment which has continuous states, continuous number of states, but fixed finite number of actions. And then we just use Q-learning. Now we use approximate Q-learning, because now instead of having the Q function as some kind of table for all the states, all the actions, it's defined explicitly. We use some kind of parametric or non-parametric function which actually defines some parametric dependency, okay, some kind of dependency between state and action pair and the Q function we assign to it. So it might be some kind of neural network, random forest, logistic regression, whatever. We just get some vector or image or tensor or something on the input, and we get number on the output. That's kind of it. But once again, we assume that we have finite number of actions, because if we have continuous number of actions, we'll actually get real problem of approximating this maximum. Because if you have continuous function and it's not convex, we don't have any guarantees on the Q function, it will be really hard to find maximum value of this Q function. Okay? So what do we have now? We've made a step from grid world, where we have finite number of states and actions, to continuous world, where we have continuous number of actions, states, but finite number of actions. So here it is. And we can actually define two architectures, possible architectures. So if we have small number of actions, we can just provide a state and ask our model, for example a network, to predict all Q values for all possible actions in the state. For example, we have 3 actions, like in Space Invaders, left, right, or fire. Okay, 4th action is just stay in the same place. And we provide only state, and our network approximates the Q value for all possible actions. It's kind of fine if we have not too big number of actions. But if we, for example, have really huge amount of actions, or if we really have some kind of continuous action space, ignoring the fact that we'll have some problems approximating the maximum value, then we can use the second architecture where we provide both state and some kind of action and predict the Q value for state action value pair, actually as we do in this formula. So we have state and action and we get just one number. In this architecture we actually provide state and get several outputs, Q for the state S and action 1, Q for the state S and action 2, 3, and so on. So I guess that's kind of clear what's going on, right? And finally, the main architecture, the main pipeline, actually it never changes. It's almost the same we had recently. So we have our new value of the Q function, reward plus gamma by maximum, and so on. And we have our current value of the Q function. We compute our mean squared error loss, then we get our loss, we get the derivative, and we update our Q function. But now we update not the Q function, but for example, assuming that it is a model, parametric model, some neural network for example, we update the parameters and we actually compute the loss derivative with respect to parameters. So that should be fine. And once again, we consider our target value because it is target constant, because actually if we won't consider our target constant, then our optimizational problem will be rather strange, because we can affect both our predicted values to fit the target, but at the same time we can actually affect our target to fit our predicted values. So we're kind of not letting our model to converge to some good behavior. Instead of that, we have a chance to ruin our targets, and that won't actually help us. Okay? So actually, yeah, that is another intuitive explanation. You should actually never affect your targets if you're speaking about supervised learning setup. And in here, after we got our new estimation of the target, we once again are in the supervised world. So we're just trying to predict the Q function without the information we got from the step explicitly. All right, so here is our objective function, just difference between our current estimation of the Q value and new estimation of the Q value based on new reward and new transition. And we can apply everything we discussed before, like Q-learning, like SERSA, like expected value SERSA. We have all the same transitions actually. So for Q-learning, our new estimation will be reward plus gamma multiplied by maximum over all the actions for the Q function. For the SERSA, we just sample action from our policy and get it. And what about expected value SERSA? How do you think? What should we have here? Just 3, 2, 1. Of course, in here we have mathematical expectation over our policy of our Q function. So nothing changes from the previous lecture. Just right now we assume that we have some parametric model which actually defines our Q function, and it can take both continuous and discrete state spaces as the input. So what kind of networks digest images well? I guess it's clear that for images we can use some kind of convolutional neural networks, and since recent achievements we can use vision transformers as well, because transformers are not rather good, they are actually great at computer vision. So we can use some kind of architecture which is well suited for computer vision problems, and then just use this architecture as some kind of preprocessor for our state input information to transform it. Here is the example architecture. So we have the observation. Observation is actually some kind of picture. Then we just use several convolutional layers, for example, or vision transformers or something to get vector representation of our state, to extract all the information from the image. And then we have this vector. We run several dense layers as well to get the Q values finally. So we predict the Q values, for example, for all the actions. And then we need to define a policy using these Q values. We can either use the softmax approach, or we can use the epsilon greedy approach, like we did on the previous class. So we get some kind of action from our policy, apply action to the environment, and then everything repeats. You see? So only difference from the previous class, now we don't have this table. Instead of that, we have the the network, which actually estimates the Q value at every step. So, actually, yeah, kind of spoiler. It looks really straightforward, and the main question, I guess some of you already have, if it's so simple, why reinforced learning is thought about as such a complex topic? Actually, all the stuff we discussed right now, like creating some kind of network for explaining, predicting the Q values for all the actions in particular states, it's kind of good idea, it's kind of beautiful idea, but it doesn't work. Like everything we discussed so far is theoretically absolutely correct, but it just won't work without a lot of duct tape and a lot of just crunches to make it work. Okay, not only crunches, but even some theoretical additions, theoretically based additions, fixes to make our model actually work better. So let's actually discuss them as well right now. Here is the first question. How bad if agent spends next 1000 ticks, so 1000 steps in the time of the environment, under the left rock? Actually, this left rock is already broken, but still it's there. So how bad is it? Actually, it will be really bad because agent will just forget how to interact with the space invaders. Because agent is all the time being trained on the experience it gets from the environment, and if it sees it, it's actually rather just safe to stay under the rock because it cannot be shot, for example, and going from this rock can cause being shot. Then actually agent, for some reason, for some time, might prefer to stay under the rock. But what happens next? Actually, after some time, the agent will just forget how to shoot at the space invaders, because if it is staying under the rock and not getting positive reward for any shooting, but getting negative reward for getting outside and being shot, then actually getting outside is equivalent to being shot. It requires agent to stay under the rock, and under the rock, agent doesn't get any additional rewards for shooting because it can't shoot anyone. So the agent is just forgetting information about the environment. While if, according to this picture, for example, It even was able to shoot some invaders at the beginning, so it did something informative. So the problem is, in general, is not under the rock and is not in Space Invaders. The problem is actually much more general. The problem is the ID property, which we have discussed for a long time. We started with the ID property at the first lecture of machine learning course. So we always want our samples to be ID. We want our distribution, which generates data on which we train, to be stable. So we train on identically distributed samples. But when we are speaking about reinforced learning, our agent behavior is actually affecting the environment and affecting the information it's being trained on. So agent got under the rock, and now it's getting only information from under the rock. So agent is actually affecting the distribution of the data it's being trained on. So samples are definitely not ID. And while model, for example, is staying under the rock, we'll actually use this cache phrase just to define some non-optimal behavior. Okay, non-optimal in global sense behavior. So while model is staying under the rock, it just forgets parts of the environment it hasn't visited for some time. So it becomes unable to behave as good as it could before. And it causes some drops on the learning curve and kind of problem. So what can we actually do to fix the problem of non-ID training samples? Once again, the problem is our agent. We have one entity of agent. It is interacting with the environment somehow, getting some information from the environment, training on this information, and then just repeat. This information is coming from this agent. So what can we do? First idea is actually relatively simple. We can try to use not only one agent, but multiple agents, which share the same parameters. So they are actually exact copies of the one original agent, like agent Smith in Movie Metrics 2 and so on. But they interact with different copies of the environment. So they actually get different experience at every step. And this experience usually will be kind of different. So then we combine all the experience they gained during one session, for example, or during one step, use all this experience to update the parameters for all the agents, and then repeat. So we get much higher chances that agents will be exploring different parts of the environment. They will behave differently. So we get more close to ID samples, because now the samples are coming from different parts of the environment and are based on different parts of the environment and on the agent, same agent. But there is a problem. We need to maintain several just environments. If we're speaking about simulators, we need to start several emulators. If we're speaking about some real-world applications, we need, for example, 10 robots instead of one robot. And in addition, we need some really heavy infrastructure to connect them together, so they share the same parameters, so they have same parameter server, and then get updated at every step, maybe every 10 steps, and so on. So here is an example. Your agent is a real robot car. What are the problems? Just try to pause the video maybe and think it over once again. You have a real car. You want to train 10 cars simultaneously. So you create 10 cars, get them out on the streets, for example. Please don't train reinforced learning cars on the real streets. And you wait for some training. Actually, the problem will be, okay, there will be a lot of problems, especially legal problems, at least right now. So please don't do that. We need some kind of polygon. And actually, if we have 10 cars, then we need actually a lot of space. For example, 10 polygons to run 10 cars. Or we need to find some way to put them at the same polygon so they don't interact with each other, and so on. And of course, we need all this hardware to solve all these hardware issues, to synchronize all the cars between each other, and so on. So multiple agents trick is rather beautiful, rather simple, rather beautiful reference to Matrix movie in here. But we have another idea from the previous class which actually can help us. And it is experience replay. We can use our own agent's experience to update the policy afterwards. So we collect some information from previous interactions where our agent had some chance to interact with different parts of the environment. We just put them in the replay buffer, and then we randomly sample some state action reward next state tuples from this replay buffer and train on these examples. So now we get much more ID information if we have big enough replay buffer. But from the other point of view, now we are training on the wiki examples from our policy as well, because some examples are coming from previous interactions in the past where our agent actually had less information about the environment, so the quality of agent's actions was lower. So it's kind of price we should pay. And here is an example for the Ethereum DQN. Yeah, the model we discussed previously. Just here it is. It's usually named DQN, Deep Q Network, because it's a deep neural network designed to predict Q values. So it's Deep Q Network. Okay, usually we'll refer it as DQN because it's kind of main name. So assume we have the Ethereum DQN where we store 100,000 of iterations. We take examples from this 101, from our replay buffer of the size, and we get really closer to ID examples we can train on. But all the directions are obtained under wiki policy, so we actually slow down the convergence at the same time. And experience replay is a technique which can't actually be applied to all the algorithms you have. Actually, it can, but it will break some assumptions. So here is an example. We approximate Q function with a neural network. We use experience replay when training, and which of these algorithms actually are able to work with experience replay and which will fail. So Q-learning, SERSA, cross-entropy method, expected value SERSA. Okay, speaking about Q function and cross-entropy method, it's kind of strange, but let's assume we're just using one of these 4 algorithms and we want to use experience replay while training. So which algorithms will fail, which will work? Just 3, 2, 1. Actually, on-policy algorithms will fail because on-policy algorithms assume that they are working under their own policy. And if we're speaking about experience replay, the experience from the policy, from the replay buffer is actually coming from different versions of the policy from previous times. So these actions and states are not generated under the current policy. So Q-learning and EV-SERSA will be actually useful when we are speaking about experience replay, while cross-entropy method and SERSA will be actually enabled to work under such assumptions because it will just affect their inner behavior. Okay, and just in case, general idea. On policy algorithms train on the examples sampled under their current policy. That's why using experience replay, where we use examples from previous wiki versions of the policy, is not actually applicable. Okay? So, just outcome. When we are training with on-policy methods, don't use or use really small experience replay buffer. Why you can actually use small experience replay buffer? Because we can assume that during just short periods of time, our policy is almost the same, so it changed only a little bit. So we almost have the same policy, almost have the same results speaking about interaction. And actually, if we're speaking about on-policy methods, we need to compensate it, for example, with parallel game sessions. So we use multiple agents to get several game sessions simultaneously and to get the experience combined together, training it. Alright, here is one fix of the non-ID problem, but there is actually plenty of different problems, so let's move on. So there is a question, left or right? Okay, in this case, I guess you can understand, according to the absence of this brick, that the ball just hits this brick and is getting back, so we should go to the right to catch it. But if we, for example, would have 2 broken bricks, then we wouldn't be able to understand whether the ball is coming to the left, to the right. We don't have any idea. So actually, we don't have enough information in the particular image to speak about the dynamics of our environment. So we need to fix it somehow. Actually, speaking about some sequential environments, for example, where we have sequence of frames, we can fix it really easily by using the n-gram trick. Yeah, n-grams, just like in NLP, when we have sequence of different states, sequence of different tokens in NLP, and here we speak about sequence of different frames, for example. And now we just combine several frames together and provide this combination as our new description of the current state of the environment. So we actually incorporate temporal information into our state description, and now our model is actually seeing not only the last frame, but sequence of frames, and it sees that actually this ball is, for example, going up and right. Actually, I guess that's not true for this particular example because we have this broken break in here. but still. So actually, if we're speaking about n-gram trick, then we are actually making the nth order Markov assumption. So we assume that the last, for example, n frames, 2 frames for example, or 4 frames, are enough to understand all the dynamics of the environment. Because if we have, for example, some dependencies which involve 5 last frames and we provide only 4 last frames, then our model is unable to capture all the needed information. So it will fail for anything longer than n frames, and it's impractical for large n, because if we need to remember 1000 frames, then it's kind of not such a good idea. It good works for some velocity timers, and actually it works good for our derivatives in terms of time. Alright, if you have 2 frames, you can estimate the velocity of the ball because you have ball in here, ball in there, so you know that it got covered this particular distance in one tick. If you have 3 frames, then you can actually estimate not the velocity but the speed of changing the velocity, the acceleration of the ball. If you have 4 frames, then you can actually estimate the acceleration of the acceleration, and so on. So what's the idea in here? If we're speaking about some short time dependencies, then we can use n-gram trick to estimate them. But in general, if we're speaking about some long time dependencies, then we of course need something else to apply. For example, we can use just recurrent formula for our environment. We can use some kind of LSTM, for example, and then every new frame is being treated as some part of the input, which is conditioned on the current state and on all the previous history as well, like we do in the natural language processing. So we can use it to fix the different different dependencies in our environment. So n-gram trick, the experience replay and multiple agent trick to fix the ID, n-gram trick to get some temporal information about the environment, and we have one additional problem which we really need to first understand because it's a really important problem, and second we need to solve it. So it's kind of general problem named autocorrelation problem, and the problem is our target is actually based on prediction, right? Because actually our model is being trained to predict the Q function, and our new estimation of the Q function is actually reward plus gamma by maximum of the Q function in the next state. And the problem is, when we are speaking about some continuous states environments, like for example Eteri, breakout, then the consecutive frames are almost the same. The environment doesn't change a lot if we just make one step further. So the ball will be slightly shifted to the bottom left, for example, bottom right, and so on. So we have 2 states. We have almost the same description of the states, and for that reason we have almost the same Q values as well, because we have state S and S prime that are really close or just exactly being copy of each other. So when we change our current prediction Q value of the state S, we are automatically changing the Q value of the state S prime as well. So actually our target is highly correlated to this prediction, and that's a problem, because actually when we use our model we use gradient descent to update our model parameters, we're updating our target as well. So on the next state, actually the next state target will be already updated along with the current state Q function. So to fix it, we actually need to break this autocorrelation problem. So our target should not be based on the prediction. And to do that, we can just do it really straightforward in a straightforward manner. So we can use, for example, 2 different networks. One to estimate our current Q function, and the second one to estimate the Q function of the future model. For example, we can just say that our Q function used for some kind of future Q function estimation, our target network, is just different. And for example, we take our current Q function, which we have right now, freeze it waits at every n steps, for example, every 500 steps, and use this estimation of our Q function to update our current Q function. Then, as you can see, our Q function won't affect the prediction on the next step by our target network, because we actually have 2 entities of our network for Q function, our network and our target network, and we just make them similar at every nth step, and then they diverge then we once again reinitialize our target network, they diverge, and so on. Or the other idea is actually to update the target network at every step, but using the exponential smoothing once again. So it's kind of always late for the original network, and original network is only slightly affecting our target network. So by this simple step, we actually break the bonds between our target and prediction, and it's really important because if we can change our target, then we actually won't be able to learn something useful. So actually here is an example, and this idea was proposed back in 2013 in paper Plain and Arrow with Deep Reinforced Learning by DeepMind. So they proposed to use 4 frames as the input and then convolutional neural network to interact with this input. Then they used just the CNN to predict Q values. Just once again, take a look. They didn't use any kind of recurrent neural networks because all the temporal information about the environment was assumed to be stored within these 4 frames. Everything else was just ignored. And then they predicted Q values, used these Q values to predict the optimal action, used some kind of epsilon greedy policy, I guess, or maybe softmax policy, and they used the experience replay buffer where they stored 1 million of the last transitions. So they tried to make the data much more closer to IID. And the target network was updated every 5,000 steps, so the autocorrelation problem was kind of fixed. So actually, that's kind of end of this lecture. It's not really long, but it actually requires some time to think over all the stuff we discussed. So actually right now we'll go through the outro, then once again get through the main points of this lecture. And of course I ask you to ask any questions on the webinar because it's a bit tricky. So first of all, Q-learning can be applied to solve the environments with both fixed number of states environments and continuous states environments, so we can do it. We haven't said anything, almost anything about continuous actions, and actually in general Q-learning is not really widely used for continuous action spaces. For that situations we usually use something like policy gradient and so on, but it will be covered on the next lectures. Or actually cross-entropy method can be used for continuous action spaces as well. We covered it on the first lecture. So please remember and most of all understand what are Q function and value function, because if you just lose the sense of them, then all the techniques we're speaking about will be really strange. And remember about ID property, because it is always important, and all the time when we use some kind of techniques to train some model on some data, we actually assume that the data is ID, because if we have really non-ID data, then training on this data is kind of useless because model is just unable to learn anything on the assumption that the data might just change at some moment by some reason, and that's it. So in reinforced learning, we definitely don't have ID assumption being true because our agent itself affects the environment, but at least we can use some kind of crunches to fix it somehow. All right, and speaking about it in general, once again, I need to recap the main idea of Q-learning. So we assume that we have the environment, but we have no idea about the dynamic of this environment, about its inner just structure, about the probability of transitions, about the reward model, and so on. So instead of trying to learn the model of the environment itself, we try to approximate the reward model, which incorporates the information about the model, about the environment model as well. So our Q function is approximating at the same time the transition model and the rewards model as well, by simply trying to remember which action delivered which result in every state. Kind of like that. And once again, we're not training our model to solve the environment directly. Instead of that, we're training our model to explain the environment in terms of the Q function. After that, we actually just exploit our Q function to get some beautiful results. So, and brief recap. So today we covered how to actually reformulate our Q-learning from tabular case to mean squared error minimization, which can be actually applied to always time I'm saying action spaces. How we can apply Q-learning to continuous state spaces. And just in case, we assume that our future cannot be affected using the gradients. You see, once again, our future estimation is kind of treated constant Actually, with target network, it is constant, and that's fine. And we just use our recurrent temporal difference formula to update our Q function. We can apply it to Q-learning, to SERSA, to expected value SERSA, actually to any Q-learning based, Q-value based approach. And we have several problems like non-ID problem, where we can use experiential replay and multiple agent trick. We have the some temporal absence of temporal information problem, which can be solved by either using the n-gram trick or by incorporating some recurrent behavior into our agent, for example, using the recurrent neural network set reason. And we have this autocorrelation problem, where two states, if they are really close to each other, might be lead to change of the target value for the particular state if we change the current version of our Q function. So just in case, to clarify this autocorrelation problem, I've got one additional example on my mind. So let's make an assumption that we have a really simple environment where we have only fixed number of states and fixed number of actions. So our Q function is just a table. So is there the autocorrelation problem present when we are speaking about tabular case? Just maybe pause the video, think about it, and then we shall discuss it. So when we are speaking about tabular case, then all the states are different by design because they are represented by different rows of our matrix. In that case, actually, autocorrelation problem is not a problem because states S and S prime, unless the model got it as the same state, are not changed anymore. Okay? So if we assume that we don't get into the original state, then actually we don't have this autocorrelation problem because target is actually not affected when we update our current Q value. So that's kind of it. So just please check for yourself that you understand really what's going on. And just in case this is not the all information about Q-learning, we'll still have additional discussions on the Q-learning because there is an overestimation problem. There are some problems with value functions and so on. So we'll have additional discussion on the Q-learning. But right now, I hope you got the main idea. We can use Q-learning to deal with continuous environments as well. And actually our Q function can be not some kind of table, but it can be any kind of function which takes state description as on the input and gives you Q values for all the actions on the output, or takes state and action pair and gives you just one number. And that's kind of it for today. Thank you for being with us on this lecture. Hope it was interesting and useful. I always appreciate your questions, so please ask any questions and take care. See you soon.